Microsoft Fabric Data Engineering Deep Dive, how OneLake, Lakehouse, Spark, pipelines, governance, and capacity shape modern data platform. Hello and welcome. Microsoft Fabric Data Engineering is the part of Microsoft Fabric focused on building the data foundation that powers analytics, reporting, data science, and AI. It helps teams collect data from many sources, store it in OneLake, transform it with Spark or low-code tools, organize it in lakehouses, optimize it as Delta tables, govern it with security and lineage, and deliver it to SQL, Power BI, APIs, and downstream applications. Microsoft Fabric documentation describes this workload as the place where organizations design, build, and maintain systems that collect, store, process, and analyze large volumes of data. In practical terms, Fabric data engineering is where raw data becomes trusted, reusable, and ready for business use. Data engineering always begins with a business need, not with a tool. A company may need reliable sales reporting, fraud monitoring, supply chain visibility, customer analytics, machine learning features, or operational dashboards. The challenge is that useful data often comes from many places, including databases, SaaS applications, files, APIs, event streams, spreadsheets, logs, and cloud storage. Data engineering turns these disconnected and inconsistent inputs into clean, structured, governed data products. In Fabric, this can be achieved with a mix of no-code, low-code, and code-first experiences, depending on the complexity of the workload. OneLake is the storage foundation of Microsoft Fabric, and it should be understood before any other Fabric data engineering concept. OneLake is a single logical data lake for the entire Fabric tenant, meaning teams can work with a common storage foundation instead of creating isolated storage silos for every project. Lakehouses, warehouses, mirrored databases, semantic models, event data, and other Fabric items can all connect through this shared foundation. This reduces duplication and makes data easier to discover, share, and govern. OneLake is not just storage, it is the common layer that enables different Fabric workloads to work together seamlessly. OneLake shortcuts are references to data that already exists elsewhere. Instead of copying data into a new lakehouse every time another team needs it, a shortcut can make external or internal data appear inside the lakehouse experience. This is useful when data already exists in another lakehouse, another workspace, or supported external storage. Shortcuts reduce unnecessary data movement, lower storage duplication, and support data mesh style sharing. They are especially helpful during migration projects because teams can connect to existing data first and redesign or move workloads gradually. A lakehouse is the primary data engineering item in Fabric. It combines the flexibility of a data lake with table-based analytics patterns that are familiar from traditional data warehouses. A lakehouse can store raw files, structured tables, semi-structured data, and unstructured content, while also exposing curated Delta tables for Spark, SQL, and Power BI. This makes it valuable for data engineers who need flexible processing and for analysts who need queryable, high-quality data. The Lakehouse is where many Fabric data engineering workflows evolve from raw ingestion to clean, business-ready data. The Fabric Lakehouse is organized into two major areas, files and tables. The files area is the unmanaged landing zone, where raw source files, CSV, JSON, Parquet, logs, extracts, and other incoming content can be stored. The tables area is the managed zone, where Delta tables reside and can be discovered by Spark and SQL experiences. This separation is important because raw data and curated analytical tables should not be mixed casually. A well-designed lakehouse uses the files area for landing and exploration, and the tables area for trusted, structured, reusable data sets. Delta Lake is the table format behind Fabric Lakehouse tables. A traditional data lake stores files, but files alone do not provide strong reliability, schema enforcement, or transaction history. Delta Lake adds a transaction log and table metadata so data can be read and written more consistently. This helps prevent problems caused by failed jobs, incomplete writes, changing schemas, and inconsistent table states. In Fabric, Delta tables make Lakehouse data more reliable for analytics, reporting, and downstream engineering workloads. The medallion architecture is a common approach for organizing Lakehouse data into bronze, silver, and gold layers. The bronze layer contains raw or lightly processed data, the silver layer contains cleaned and standardized data, and the gold layer contains business-ready data for reporting and analytics. This pattern gives teams a clear progression from source data to trusted consumption. It also simplifies troubleshooting because engineers can identify whether a problem originated in ingestion, cleansing, or business modeling. Fabric supports this architecture through Lakehouse folders, Delta tables, Spark, Dataflows Gen2 pipelines, and Materialized Lake Views. The bronze layer is the first layer of the Lakehouse and should preserve source context. This includes maintaining information about where the data originated, when it arrived, which pipeline loaded it, and whether it was part of a full or incremental load. Bronze data may still contain duplicates, missing values, inconsistent naming, or raw source structures. That is acceptable because the purpose of the bronze layer is traceability and replayability, not final business quality. If downstream logic changes, engineers should be able to rebuild silver and gold datasets from the bronze layer. The silver layer is where raw data becomes clean and reusable. In this layer, engineers standardize data types, rename columns, remove duplicates, validate keys, normalize values, and apply shared business rules. A silver customer table, for example, should contain consistent customer identifiers, cleaned names, standardized addresses, and reliable attributes that multiple teams can reuse. Silver data is not always the final reporting model, but it should be trustworthy enough to support many downstream use cases. A strong silver layer prevents individual report teams from repeatedly implementing the same data cleaning logic. The gold layer is designed for consumption. This is where data is shaped into fact tables, dimension tables, aggregates, KPI tables, and report-ready datasets. A sales-focused gold layer, for example, may include sales fact tables, customer dimensions, product dimensions, date dimensions, employee dimensions, and monthly revenue summaries. Gold data should align with agreed business definitions so users clearly understand what each metric represents. This layer powers Power BI reports, executive dashboards, operational analytics, regulatory reporting, and, in some cases, AI or application workloads. Fabric provides multiple ways to bring data into a lakehouse, and selecting the appropriate option is an important part of data engineering design. Engineers can use file uploads, load to tables, copy activity, copy job, Dataflows Gen2, Eventstreams, mirroring, notebooks, Spark job definitions, and shortcuts. The best choice depends on the source system, data volume, refresh frequency, transformation complexity, and the technical skill set of the team. A batch database extract, a real-time event stream, and a one-time CSV upload should not be handled in the same way. Fabric offers different tools to support these different ingestion patterns. Load to tables is useful for simple file-to-table scenarios. When a user uploads or selects a supported file, Fabric can convert it into a Delta table that appears in the Lakehouse tables area. This is helpful for quick starts, prototypes, small control datasets, and straightforward reporting scenarios. However, production-grade data engineering often requires repeatability, validation, parameterization, error handling, and monitoring. For that reason, larger or business-critical ingestion patterns are usually better implemented through pipelines, notebooks, Spark job definitions, or Dataflows Gen2. Pipelines are Fabric's visual orchestration tool for coordinating data workflows. Orchestration refers to controlling the order, dependency, scheduling, and execution of multiple processing steps. A pipeline can copy data, run notebooks, trigger Spark job definitions, call stored procedures, invoke web activities, and coordinate validation or notification tasks. Pipelines are especially useful when a process must run repeatedly and reliably. They also provide execution history and monitoring capabilities, which are essential for production operations and operational support. Copy activity is a pipeline activity designed for controlled data movement. It can move data from supported source systems into lakehouses, warehouses, and other destinations. It works well for historical loads, scheduled ingestion, database extracts, cloud file transfers, and medallion-style ingestion patterns. Copy activity offers more flexibility than simple replication because it can operate as part of a larger pipeline with dependencies, monitoring, and error handling. It is a strong choice when a team requires local data movement combined with orchestration and operational control. Copy job is designed to simplify ingestion when users need more than basic mirroring but do not want to build a full pipeline manually. It supports bulk copy, incremental copy, and change data capture patterns where supported. Change data capture identifies changes in a source system, such as inserts, updates, and deletes, so the destination can remain current without reloading all data repeatedly. Copy job is useful for multi-table ingestion, scheduled refreshes, and guided configuration experiences. It is a practical option when both ease of use and incremental data movement are important. Mirroring is a near real-time replication approach for supported operational databases. Replication means copying changes from a source system into Fabric so analytics teams can use the data without directly querying the production database. This is valuable when business users need fresh data while the operational system must remain protected from heavy analytical workloads. Mirroring is designed to reduce setup complexity compared to building custom ingestion pipelines. It is best suited for supported source systems where the required behavior aligns with the mirroring model. Dataflows Gen2 provide a visual, low-code data preparation experience based on Power Query. Dataflows can connect to data sources, profile data, clean columns, merge datasets, apply transformations, and load results into destinations such as lakehouses. They are useful when the transformation logic is business-oriented and can be managed visually. Dataflows Gen2 are especially valuable for analysts, data integrators, and engineers who want repeatable data preparation processes without writing Spark code. For extremely large-scale or highly customized distributed transformations, Spark may be the more suitable option. Eventstreams support real-time ingestion and routing. Real-time data arrives continuously, such as telemetry, clickstream events, IoT messages, application logs, customer service interactions, or operational signals. Event streams can ingest events, apply lightweight transformations, and route them to destinations such as Lakehouse, Event House, Activator, or custom endpoints. This enables scenarios where decisions and actions must occur quickly instead of waiting for scheduled batch processing. Event streams complement batch pipelines rather than replacing them. Apache Spark is the distributed processing engine used for complex Fabric data engineering workloads. Distributed processing means computational work can be divided across multiple compute resources, so large datasets can be processed in parallel. Spark is useful for large joins, aggregations, data cleansing, enrichment, semi-structured data processing, machine learning preparation, and streaming workloads. Fabric supports Spark through notebooks and Spark job definitions. Engineers can use PySpark, Spark SQL, Scala, and R, depending on workload requirements and team expertise. Fabric notebooks are interactive documents that combine code, SQL, visual output, and explanatory text. They are useful for exploring raw data, testing transformations, creating delta tables, validating results, and documenting logic. A notebook can support both development and production workflows when managed correctly. Well-designed production notebooks should be modular, parameterized, version-controlled, and thoroughly tested. They should not rely on manual user actions or hidden assumptions. Spark job definitions are used when Spark code needs to run as a production-oriented job rather than as an interactive notebook session. A Spark job definition can reference files, arguments, lakehouses, and runtime settings, so the workload executes consistently each time. This is useful for repeatable ETL, batch processing, structured streaming, and packaged Spark applications. ETL stands for extract, transform, and load, while ELT stands for extract, load, and transform. Spark job definitions are especially valuable when engineering teams want a more structured, application-style deployment pattern. Fabric environments help standardize Spark runtime settings, libraries, and compute configurations. An environment is a managed configuration that can be reused across notebooks and Spark job definitions. This prevents developers from manually installing different package versions or modifying Spark settings independently. Environment management improves reliability because production workloads require consistent dependencies and configurations. In enterprise projects, environments should be treated as controlled engineering assets with proper governance and change management. Spark runtime versions define the core software stack used by Spark workloads. A runtime includes versions of Spark, Delta Lake, Python, Scala, Java, R, and related libraries. Runtime selection is important because code compatibility, library behavior, and performance characteristics may change between versions. Before upgrading a production runtime, teams should test notebooks, Spark job definitions, dependencies, and Delta table behavior carefully. Runtime governance helps reduce the risk of unexpected failures after upgrades. Spark pools and Fabric capacity should be understood together. A Spark pool defines the compute configuration options for Spark workloads, while Fabric capacity represents the purchased or assigned pool of resources that powers Fabric workloads. Capacity is measured by SKU and determines how much compute is available across workloads such as Spark jobs, pipelines, warehouses, reports, and semantic models. If many workloads run simultaneously, they may compete for available capacity. Effective capacity planning helps prevent slowdowns, job queuing, and unreliable refresh behavior. Spark structured streaming enables continuous data processing into Lakehouse tables. A streaming job reads incoming data as it arrives, processes it, writes it in Delta format, and uses checkpointing to track progress. A checkpoint is metadata that allows the stream to restart without losing its position in the data stream. This capability is important for reliability because streaming jobs may stop, fail, or restart during operations. In production environments, structured streaming requires monitoring, retry policies, checkpoint management, and clear operational ownership. The SQL Analytics endpoint is automatically created with the Fabric Lakehouse. It provides a read-only T-SQL query experience over Lakehouse Delta tables. Read-only means users can query the data, but they should not use this endpoint to insert, update, or delete records in the Lakehouse. The SQL Analytics endpoint is useful for analysts and business users who are comfortable with SQL and do not need to work directly with Spark code. It also supports data exploration, semantic model creation, and reporting access. The SQL Analytics endpoint connects data engineering workflows to business intelligence workflows. Data engineers can use Spark pipelines or Dataflows Gen2 to create curated Delta tables, while analysts use SQL to inspect and query those same tables. Power BI can then build semantic models and reports from the curated Lakehouse data. This creates a clear separation of responsibilities. Engineering tools create and maintain trusted datasets, while SQL and BI tools consume them for analytics and reporting. The result is reduced duplication and a smoother transition from data preparation to business insight. Fabric Lakehouse and Fabric Warehouse are related technologies, but they serve different purposes. A lakehouse is best suited for Spark engineering, big data processing, semi-structured and unstructured data, machine learning preparation, and medallion architectures. A warehouse is better suited for schema-first data warehousing, relational modeling, structured data, and full T-SQL warehouse patterns. Many organizations benefit from using both instead of forcing every workload into a single storage model. A common approach is to transform and prepare data in the Lakehouse, then expose highly curated SQL models through a warehouse or semantic model. Choosing the correct Fabric data store depends on the workload requirements. A Lakehouse is well suited for data engineering and data science workloads. A warehouse is ideal for enterprise SQL analytics and dimensional modeling. Eventhouse is designed for high-volume event and time series analytics. SQL database in Fabric supports operational transactional scenarios where application-style relational data is required. Cosmos DB in Fabric, where available, supports NoSQL and application-oriented workloads. The most appropriate store should align with the data structure, query patterns, latency requirements, and developer skill sets involved. Lakehouse schemas organize tables into logical groups. A schema is a named collection of tables, such as sales, finance, marketing, operations, or human resources. Without schemas, large lakehouses can become difficult to navigate because every table appears in a single flat list. Schemas improve discoverability, naming consistency, and domain organization. They are also important for advanced lakehouse capabilities, such as Materialized Lake Views and structured cross-workspace references. Cross-workspace querying allows engineers to reference data from multiple workspaces when permissions permit access. With schema-enabled lakehouses, Spark XUO can use multi-part naming conventions that identify the workspace, lakehouse, schema, and table. This enables teams to build domain-oriented data platforms where different business groups manage their own lakehouses independently. For example, a finance workspace could query approved sales data from a sales workspace without duplicating the underlying data sets. This pattern supports collaboration while reducing unnecessary data duplication. The Lakehouse Explorer is the primary interface for working with Lakehouse data. Users can browse the tables and files areas, preview data sets, inspect table files, upload content, create folders, manage shortcuts, open notebooks, create semantic models, and switch to the SQL Analytics endpoint. This interface makes Lakehouse operations accessible to both code-first engineers and users who prefer visual navigation. It also helps teams inspect and troubleshoot data quickly during development and operational support. A well-structured Lakehouse Explorer experience usually reflects a well-organized Lakehouse architecture. Automatic table discovery enables Fabric to recognize valid Delta tables stored in the Manage Tables area. When tables are written correctly, Fabric can register them so they appear consistently across Spark, XELA, and Lakehouse experiences. If invalid files or unsupported folder structures are placed inside the tables area, they may appear as unidentified or unsupported content. For this reason, raw files should generally remain in the Files area, while valid Delta tables should be stored in the Tables area. Proper organization improves clarity, governance, and maintainability. Semantic models transform curated Lakehouse data into analytical models for Power BI and other reporting experiences. A semantic model defines tables, relationships, measures, calculations, and business logic that reporting users depend on. Direct Lake mode can allow Power BI to work directly against OneLake data in supported scenarios, reducing unnecessary data imports and duplication. This creates a faster and more efficient path from Lakehouse Delta tables to business reports and dashboards. However, the semantic model still requires careful design because it determines how business users interpret and interact with the data. Relationships in semantic models must be designed carefully. A fact table contains measurable events, such as sales transactions, while dimension tables contain descriptive context, such as customer, product, employee, geography, or date information. The relationship keys, cardinality, and filter direction determine how Power BI calculates and aggregates results. If these relationships are configured incorrectly, reports can display misleading totals and inaccurate analytics even when the underlying tables are correct. Effective data engineering includes a strong semantic modeling handoff to ensure reporting accuracy. Performance begins with table design. Engineers should choose efficient storage formats, avoid creating unnecessary small files, partition data only when it provides clear benefits, and design tables around actual query and reporting patterns. Many performance issues are caused by poor data layout rather than insufficient compute resources. A poorly designed table can negatively affect Spark workloads, SQL queries, and Power BI reporting performance. Strong Fabric engineering requires thinking carefully about how data will be queried, refreshed, joined, filtered, and maintained over time. VORDER is a Fabric optimization for Parquet file layout. Parquet is a columnar file format widely used for analytics workloads, and VORDER improves how data is organized to support faster reads and better compression in supported scenarios. This is especially beneficial for analytical queries and reporting workloads that repeatedly scan large datasets. The trade-off is that write operations may require additional processing time. VORDER should therefore be enabled when the read performance improvements justify the additional write overhead. Optimized write helps reduce the small file problem in distributed storage systems. Small files are inefficient because processing engines spend excessive time opening, listing, and scheduling work across many tiny pieces of data. Optimized write attempts to generate fewer, larger files, which improves downstream query performance and storage efficiency. This is particularly useful for partition tables and workloads with frequent write operations. Even with automatic optimization enabled, teams should continue monitoring file counts and table sizes because automated features do not replace proper engineering oversight. Delta table maintenance becomes increasingly important as data volumes grow. Frequent incremental loads, merges, updates, and deletes can gradually create fragmented files and inefficient table layouts. Maintenance operations such as compaction and optimization help reorganize files to improve query and processing performance. Vacuum can remove old files that are no longer referenced by the Delta transaction log, but retention settings must be managed carefully. Removing files too aggressively can interfere with time travel, rollback operations, or concurrent readers that still depend on older file versions. Partitioning is a table layout technique that stores data in folders based on column values. It can improve performance when queries frequently filter on those columns, such as year, month, region, or business unit. However, partitioning is not automatically beneficial in every scenario. Over-partitioning can create too many folders and small files, which may actually reduce performance and increase management overhead. Large fact tables often benefit from partitioning, while smaller dimension tables usually do not require it. Materialized lake views provide a managed approach for storing refreshed transformation results over lakehouse data. A materialized view pre-computes data instead of recalculating expensive transformations every time a query runs. This is especially useful for bronze to silver transformations, silver to gold aggregations, and frequently reused in analytical datasets. Fabric can manage refresh behavior and dependencies for these views automatically. Materialized lake views help improve consistency, query performance, and data reuse across engineering workloads. Data quality is a fundamental responsibility in data engineering. Teams should validate row counts, null values, duplicate keys, schema changes, valid ranges, referential integrity, and data freshness. For example, a sales data set should validate invoice dates, customer keys, product keys, revenue amounts, and whether incremental loads completed successfully. Data quality checks can be implemented using Spark SQL, notebooks, pipelines, materialized lake views, or custom validation frameworks. Reliable analytics and reporting depend on strong and consistent data quality controls. Monitoring is essential for production data engineering environments. Pipelines may fail, source schemas may change, Spark jobs may slow down, or Fabric capacity may become constrained. Fabric monitoring experiences help teams inspect pipeline runs, Spark application details, job history, execution status, and operational metrics. Teams should monitor failures, execution duration, retry counts, input and output row volumes, data freshness, and capacity utilization. A data platform can only be considered reliable when its operational health is visible and measurable. Spark monitoring and Spark Advisor help diagnose performance and reliability issues. Spark workloads can struggle because of skewed data, inefficient joins, excessive shuffle operations, memory pressure, poor partitioning strategies, small file problems, or dependency conflicts. Monitoring helps engineers identify the true bottleneck instead of relying on assumptions. This is important because simply adding more compute resources may not solve a poorly designed Spark job. Effective Spark engineering combines well-structured code, efficient data layout, and strong operational diagnostics. Governance must be designed from the beginning. Governance means understanding what data exists, who owns it, where it originated, how it is protected, and whether it is trusted. Fabric integrates with Microsoft Purview capabilities such as sensitivity labels, lineage, endorsement, discovery, and policy-based governance. This is important because Lakehouse data may support executive dashboards, regulatory reporting, machine learning models, and AI applications. Without proper governance, a lakehouse can quickly become another uncontrolled data swamp. Security in Fabric data engineering operates across multiple layers. Workspace roles control broad access to Fabric items and experiences. OneLake security and data access roles can enforce permissions closer to the storage layer. SQL Analytics endpoint permissions can govern access through T-SQL interfaces. Sensitivity labels classify data so users understand protection and compliance requirements. Shortcuts must also be secured carefully because they can expose data stored in other locations or workspaces. A secure architecture considers every possible path users can take to access data. Lifecycle management introduces software engineering discipline into data engineering processes. Notebooks, pipelines, Spark job definitions, environments, semantic models, GraphQL items, and Lakehouse metadata should all be version controlled, reviewed, tested, and promoted through controlled deployment stages. Git integration helps track changes over time, while deployment pipelines support the movement of artifacts between environments and workspaces. Actual Lakehouse tables and stored data should not be managed the same way as code artifacts, so teams must clearly separate artifact deployment from data preservation strategies. This separation helps prevent accidental overwrites and supports safer production releases. Workspace separation is a practical operational model for enterprise data platforms. Development workspaces are intended for experimentation and active development. Test workspaces support integration testing, performance validation, security reviews, and user acceptance testing. Production workspaces host stable, governed, and monitored workloads that support business operations. This separation reduces the risk that experimental changes could disrupt trusted reports, pipelines, or production datasets. Deployment pipelines and Git integration support this operating model, but teams still require strong review, approval, and release management practices. Naming standards make Fabric environments easier to manage and maintain at scale. Teams should define consistent naming conventions for workspaces, lakehouses, schemas, tables, notebooks, pipelines, Dataflows Gen2, Spark job definitions, environments, semantic models, and reports. Standardization should also include bronze, silver, and gold layers, checkpoint folders, archive locations, rejected record folders, and pipeline naming patterns. Clear naming conventions reduce confusion, improve discoverability, and simplify troubleshooting. Poor naming practices can become a significant operational problem as the number of assets and teams increases. Documentation should be part of every data engineering workflow. Each important data set should include a clearly identified owner, business purpose, source description, refresh frequency, data quality expectations, sensitivity classification, and known limitations. Business users need to understand which tables are trusted and what each metric represents. Engineers require documentation to support maintenance, troubleshooting, onboarding, and long-term platform sustainability. Reports, APIs, and AI systems all become more reliable when the underlying data products are clearly defined and documented. The Livy API supports remote Spark execution against Fabric Spark compute resources. Livy allows external clients, automation tools, or developer environments to submit Spark session jobs or batch jobs to authenticated API calls. A session-based job is useful for interactive execution scenarios, while a batch job is better suited for scheduled or submitted workloads. Using Livy requires Microsoft Entra authentication, appropriate workspace permissions, and a valid Lakehouse context. Livy is especially valuable when organizations need advanced automation or integration with external engineering workflows and orchestration systems. VS Code integration supports developers who prefer local development tools and workflows. Instead of performing all development activities within the Fabric browser experience, engineers can use familiar local development practices for notebooks, Spark job definitions, lakehouse exploration, and related engineering tasks. This supports stronger code review processes, reusable code structures, local editing preferences, and improved developer productivity. Fabric continues to provide the managed platform experience, while VS Code integration helps professional engineering teams apply modern software engineering practices to data engineering projects. API for GraphQL provides an application-oriented method for exposing Fabric data. GraphQL enables applications to request only the specific fields and relationships they require instead of directly querying raw tables or retrieving unnecessarily large datasets. This capability is useful for internal portals, business applications, operational systems, and AI-enabled workflows. It creates a structured and controlled access layer over curated enterprise data. When combined with source control, governance, and deployment practices, GraphQL can become an important component of the broader Fabric data and application engineering lifecycle. GraphQL is also important for AI-oriented scenarios. AI applications and intelligent agents require governed, understandable, and discoverable access to enterprise data. A structured API layer can expose only the information necessary for a specific task instead of granting broad access to underlying tables or datasets. This approach does not replace the need for data quality, governance, or security controls. Instead, it extends the Fabric data engineering foundation by making curated enterprise data easier, safer, and more manageable for applications and AI systems to consume. Migrating from Azure Synapse Spark to Fabric Spark requires careful planning. The platforms differ in pool architecture, runtime versions, configurations, library management, notebooks, Spark job definitions, security models, DevOps processes, and monitoring capabilities. Fabric Spark is designed around OneLake, environments, starter pools, high concurrency, V-order optimization, deployment pipelines, and capacity-based scaling. Some Synapse capabilities may not map directly to Fabric experiences or operational models. A successful migration therefore requires code testing, dependency validation, performance benchmarking, and operational redesign. Capacity planning affects every serious Fabric implementation. Capacity represents the shared compute resource that powers Fabric workloads, which means Spark jobs, pipelines, semantic models, warehouses, reports, and other services may compete for the same underlying resources. Teams should understand workload concurrency, queuing behavior, refresh schedules, peak usage periods, and skew limitations. A solution that performs well for a single developer or demonstration workload may fail under real enterprise scale usage when many workloads run simultaneously. Production architectures should always be validated under realistic operational load conditions rather than only in small scale test scenarios. A complete fabric data engineering architecture usually begins with source systems such as operational databases, SaaS applications, APIs, flat files, cloud storage platforms, and event streams. Data enters Fabric through shortcuts, mirroring, copy job, copy activity, Dataflows Gen2, event streams, notebooks, or Spark job definitions. The data lands in the bronze layer, is cleaned and standardized into the silver layer, and is transformed into business-ready datasets within the gold layer. SQL analytics endpoints, semantic models, Power BI reports, GraphQL APIs, data science workloads, and AI applications then consume this governed and curated data. This end-to-end flow is what transforms raw information into actionable business value. The final takeaway is that Microsoft Fabric Data Engineering is not just a Lakehouse platform, not just Spark, and not just pipelines. It is a connected operating model for modern enterprise data platforms. OneLake provides the unified foundation. Lakehouses organize engineering workloads. Delta tables provide reliability and transactional consistency. Spark handles complex distributed processing. And pipelines and data flows Gen2 manage orchestration and movement. SQL analytics endpoints and semantic models support data consumption, while governance and security capabilities help keep the platform trustworthy and manageable. When these components are designed and operated together, Fabric becomes a powerful foundation for analytics, reporting, data science, and AI-ready enterprise data solutions. Thank you for taking the time to explore this topic.